Dear learners, welcome to the course Electromagnetic Fields. Generally, spatial derivatives performed on both scalar and vector fields. If the spatial derivatives considered for scalar field, it will lead to the definition for gradient of a scalar. If the spatial derivatives are considered in vector field, which lead to the definition for divergence of a vector and curl of a vector. In this video, we are going to talk about divergence of a vector. This figure illustrates flux lines or vector fields. What is meant by flux lines? Flux lines or strain lines. In the study of vector fields, it is convenient to represent field variations graphically by directed field lines, which are called flux lines or strain lines. The direction of vector field is indicated by the directed lines or curves which are illustrated in this figure. So you note down here in the region A more number of lines with the equal length of lines. The length of lines are equal. At the same time, a higher density of field lines are here in the region A. You observe that in the region B has less number of flux lines. So, the field in region A is stronger than in region B because of the higher density of field lines or flux lines in the region A. In this figure, it illustrates the field lines are away from the point Q. It is radially outward from that point Q. This field is called as a radial field. The field is strongest in the region closest to Q. The point Q, the region is very strong compared to other regions. This figure illustrates the uniform field. The uniform field, we observe that all flux lines are equal in length and moving in direction, for a direction, it has a same magnitude. It is called as a uniform field. The vector field strength in this figure is measured by the number of flux lines passing through a unit surface normal to the vector. The flux of a vector field is analogous to the flow of an incompressible fluid such as water. The divergence of vector field at point P is a measure of how much the field vector diverges or converges from that point. This is illustrated in this figure. The first figure A, it represents the positive divergence. Positive divergence, the divergence of the vector field at point P is a measure of how much the field diverges from the particular point. If the field is diverging from the point P, then the divergence of is positive. In the second figure, all the field lines are converging at point P. Therefore, it is a negative divergence. It has a negative divergence at point P. It means that there is a presence of sink. The positive divergence means it indicates the presence of source. Negative divergence means it indicates the presence of sink. The third figure C, it illustrates the zero divergence at point P. That means whatever the flux lines converge at point P, diverging at same will be diverging at point P. Therefore, the divergence is zero at point P. That means there is no source or sink at point P. So, from this figure, we can understand the physical meaning of the divergence of a vector. The divergence of a vector at a given point P is the outward flux per unit volume over a closed incremental surface as the volume shrinks about the point. This is the definition for the divergence. It just defines the outward flux per unit volume over the closed surface as the volume shrinks about the point P. Mathematically, divergence of a vector can be written as surface integral of a vector or ds vector divided by incremental volume as the volume tends to 0. Some examples of divergence of vector. The first example, Leaking air from a balloon yields a positive divergence. For the negative divergence, the best example is a rushing of air into the drum under the carriage of a train. Here I am going to explain the physical meaning of the divergence with one small example. We consider a tube of a vehicle at a pressure. A vehicle in which air is practically consider a tube of vehicle in which air is filled with a pressure. It is shown in figure U. In the B, we consider punctured tube. Suppose if we puncture the tube, the air inside the tube tries to rush out from the tube through a small hole. So now the velocity, air velocity inside the tube is greatest than at the air velocity in the outside. Therefore, there is a positive divergence exists at point P here. So from this figure B, we can see that the air velocity is a function of a distance, and hence the divergence velocity is positive. The density of lines near the hole is high. It means that a higher air velocity. The source of such velocity lines is throughout the tube, and hence anywhere inside the tube. At any point, the divergence is positive. The third figure, it illustrates for the hollow tube. If there is a hollow tube, it opens from both ends. The air enters from one end and passes through the tube and leaves from the other end. The velocity of air is constant everywhere inside the tube. In such a case, the divergence of velocity field is zero inside the tube. So from the discussion, we came to the conclusion that a positive divergence for any vector quantity indicates the source of that vector quantity at that point. A negative divergence of any vector quantity indicates a sink of that vector quantity at a particular point. A zero divergence indicates there is no source or sink exists at that point. So as a result of the divergence of the vector field is a scalar. The divergence indicates how much flux lines are leading from a small volume per unit volume, and there is no direction associated with the divergence. So divergence of a vector field is a scalar quantity. We shall now derive the expression for the divergence of a vector in Cartesian coordinates. Let us consider the differential volume element in Cartesian coordinate system with the sides of dx, dy, dz along x, y and z directions respectively. We are going to evaluate divergence at point P of x0, y0, z0. So in this figure, it shows the net increase in positive y direction, and this is in the positive x direction, and it is in the positive z direction. Already we know that how to write the vector in Cartesian coordinate system. We can write a vector is equal to ax vector plus ay vector plus az vector. So from the divergence of a vector, first we have to evaluate the surface integral of the vector quantity. Surface integral of a vector dot ds vector. This surface integral can be decomposed into 6 surfaces. Since the figure, it consists of 6 surfaces. One is a front surface and a back face, right hand side and left hand side, top and bottom surfaces. It consists of totally 6 surfaces. Therefore, the surface integral can be decomposed into 6 surfaces. The net increase of flux in the y direction is ay plus dou ay by dou y, del x, del z minus ay, del y, del z. So therefore, the net increase of flux in y direction is dou ay by dou y, del x, del y, del z. Similarly, the net increase of flux in z and x directions are dou az, dou z, del x, del y, del z, and dou ax by dou x, del x, del y, del z respectively. Consequently, the field increase is given by So now we substitute the net increase in x, y and z directions in the surface integrals. We will get dou ax by dou x plus dou ay by dou y plus dou az by dou z. By the definition of a divergence, we can write divergence of a vector is equal to dou ax by dou x plus dou ay by dou y plus dou az by dou z. It is mathematically represented as del dot A vector, that is spatial derivatives of vector quantity, is nothing but divergence of A vector, del dot A vector. In cylindrical coordinate system, the same way we can obtain the expression for del dot A vector, 1 by r dou r ar by dou r plus 1 by r dou a5 by dou 5 plus dou az by dou z. In spherical coordinates, as del dot A vector is equal to 1 by r squared dou by dou r squared ar plus 1 by r sin theta dou a theta sin theta by dou theta plus 1 by r sin theta dou a5 by dou 5. In this way, we can write any vector quantity in Cartesian coordinate system, cylindrical coordinate system and spherical coordinate systems. Divergence of a vector is a scalar. Properties of divergence of vector is listed here. Divergence tells us how much flux is leaving a small volume on a per unit basis. Here no direction is associated with this. Second one is the divergence of a scalar has no meaning. Say for example, if S is a scalar field, then del dot M has no meaning. Note that del operator can operate on scalar field, but the dot product has no meaning. Divergence of a scalar has no meaning. Third property is del dot A vector plus B vector is equal to del dot A vector plus del dot B vector. Another most important property is if the divergence of any vector field is 0, then the vector field is said to be solenoidal field. Mathematically, it is represented as del dot A vector is equal to 0 for A vector to be solenoidal. I hope you would understand the divergence of vector in detail. Thank you.